Good afternoon, everyone, and welcome to BSides Las Vegas, Breaking Ground. This talk is Virtualizing Breakpoints on x86 64, and it's presented by Gregory Price. A couple announcements before we begin. I want to say thank you to our sponsors, especially our Inner Circle sponsors, Critical Stack and Valamail, and our stellar sponsors, Amazon, BlackBerry, and Cylance, and Robinhood. So without our sponsors and our donors and our volunteers, this would not be possible. So big thank you to them. Another announcement before we get started is this talk is being recorded and streamed to YouTube. So if you have any questions, please raise your hand and I'll bring the microphone over so that YouTube can hear you. Also, please be sure to silence your cell phones out of courtesy for others. So yeah, let's get started. Thank you.
Cool. Thank you very much. So yeah, this is my talk on virtualizing breakpoints for x86. A little bit about me to begin with. I'm a hypervisor and emulation developer at Raytheon Codex. I've got a background in computer science. I got my BS and MS from Northeastern. And I spent about 6 years in the US Navy doing network analysis before I eventually went on to the position that I have now. And I only say that for any vets that are in the audience. You know, if I did it, you can do it too. You can make the transition, and it works out well. A special thanks to the Northeastern University HPC lab for helping me to develop the solution that I'm going to talk about today and to develop this talk as well. So the first thing I'm going to start off with is a little demonstration. On this screen, I have this really compelling piece of software here that does basically nothing, because if you can read it, it does a simple comparison, and it's checking to see if 0 equals hex CC. And so we should never, ever see this print statement occur. But if I set a breakpoint on this program at a special place, 53F, and I run the program, we run into two things here that are kind of interesting. You can see, one, I have printed out the thing I am not supposed to be able to print, and two, we didn't actually break in this program. So the question is, why does this occur? The answer is actually pretty simple. On x86 and in most platforms, we use a form of binary replacement breakpoint. And what this means is that we're actually replacing the instruction in memory with, in this case, an int3 instruction, which is one single byte, hex CC. The problem with this, though, is that if you choose the wrong spot in the instruction to breakpoint, you simply corrupt the instruction. And so that's what I've done here on this program, is I've actually modified this instruction here by using an offset breakpoint such that I replace that 0 with hex CC. And that's why we get the result that we have here. Now, this is kind of an interesting problem, and it was one that, as I was helping to develop a hypervisor platform that we write, we had kind of a small slip-up where we had loaded some wrong symbols, and we were causing the guest OS to crash. Now, we were looking for bugs in the OS, so we were like, woo, we got it to crash. But then we realized what the problem was, and we were really concerned about solving this for the future. It took a couple of months, but after a couple of months, we realized you can't actually solve the problem of where it is safe in memory to breakpoint, because you have no idea what the program is attempting to do. And so that's what we're going to talk about a little bit today. And what I call this problem is the critical byte problem. Basically, there's a critical byte in an instruction that we have to hit, and can we solve this critical byte problem? So one quick caveat to this talk, what I'm going to talk about and the design for this solution is not, quote unquote, the solution. Right? There are many different ways we could implement this solution, so I don't want you to walk away saying that this is the only way to do this. My hope is that you walk away thinking ultimately that we're being ruled by some debugger rules of the past, and we need to change the underlying hardware to create new forms of debuggers. So, but before we can get into that, I do want to prove to you a little bit that we can't just use other forms of breakpointing methods. So we're going to do a quick review of how we do breakpointing across all different types of debuggers. The most common one on most architectures is a form of binary replacement. So we already went over that. But there's also this idea of single stepping and branching. And this is basically implemented via a special flag in, for example, the R flags register, or a special MSR that lets you do single branching instead of single stepping. And the idea is you set this trap flag, you hand the processor back to the program, it runs a single instruction or runs up to a single branch, and then it will break and give you a chance to interpose once again. So that's one example of another form. Another thing that most people are familiar with, if you're an embedded developer using JTAG, usually most architectures provide some form of breakpoint registers. It's these simple comparison registers in memory that when you enable them, allow you to break on an address, whether it is on execute or on read-write, etc. Usually this is limited in scope or limited in availability. Most architectures provide somewhere between 4 and 8 debug registers. On x86, we get 8, and the configurability is rather limited. You can only set breakpoints on up to 8 bytes in memory, and the configuration doesn't let you set a breakpoint on execute, read, and write. You have to pick just a couple of those features. So there's some limitations there. Another form of debugger or another form of system that we utilize to debug programs is emulation. And this is basically we're going to interpose on every single instruction that runs. And this is just a sample list of ways that I can imagine in the process of emulating an instruction what I might want to do, right? I might want to break in and do something on instruction fetch. I might want to break in and do something on memory write, or maybe I have some data flow type analysis going on and I want to see when the value of RAX, and if we're jumping to RAX, if that RAX register contains user-controlled data, for example. So we can come up probably with a list that's like 100 or 200 times longer than this of ways that I would want to interpose. And finally, kind of the hot area of research in recent years, you'll see a lot of papers talking about dynamic binary instrumentation, or DBI. And this is kind of an amalgam of all of these different techniques. It's basically we're going to use binary replacement here, we're going to use emulation here. When that doesn't work for us, we're going to use breakpoint registers to optimize things. Maybe we're going to add some special trampolines to the code, and it's a combination. One example of this to drive this home is there was a paper from like 2012 or 2013 called Spider Stealth Breakpointing. And the goal of this paper was to make sure that a program couldn't see when a breakpoint is being set on basically to prevent detection of a debugger there. And the way they did this, they built a rather complex system. Not that it's bad, it does a very good job, but they have to have this code modification handler so that if you have a piece of malware that's trying to relocate itself in memory, it's no longer safe to breakpoint those areas of memory, so you have to detect that. You have these different cache views between a data view and an instruction view based on whether or not that page is being used to execute or you're trying to read from that page. And you actually have to use special page table management in order to implement this whole solution. So very complex and very low level. It has to be done in a kernel driver. It's not something that we could necessarily expose to a user land debugger, for example. So there's some limitations there. And other people have tried to solve this problem that I'm proposing here, this critical byte problem, this idea that I don't want my breakpoints to be detectable, and I don't want my breakpoints to corrupt the program. And so I have a list of papers here that I've done some background reading on, but really the problem that they're all trying to solve is the same one, and all of this reduces to the halting problem. And so you can't actually solve and determine where in memory it is safe to breakpoint if you're using binary replacement. If you kind of abstract it out, what you're really talking about is how do I determine something behavioral about a generic program? And if you have any computer science background, you're running straight into the halting problem. You shouldn't even attempt to solve this problem because it's a non-decidable problem. So if we look at, throwaway slide there, but so if we look at these breakpoint constructs that we have here, we can kind of pick a lot of these apart as to why this one's not quite appropriate to use here, this one's not quite appropriate to use there. And the reality is they really do all suck in some way. Either they're corruption prone or they're slow, we have a limited number of breakpoint registers, or they're slow and complex, or they're extraordinarily complex and they'll never make it into modern day tools because the adoption is very limited in scope. And so the question that I'm kind of asking is there something that we can implement, a new extension to the system that we can implement that will allow us to both solve this problem or do away with this problem and build better debuggers for the future? So one extra thing here is the question that I started with was, when did someone last review breakpoint technology? When did advancement in this area kind of stop? And so there's this paper called A Survey for Supporting and Implementing Debuggers from 1990. And I picked out some choice quotes from this where they talk about replacing the instruction and single-stepping and instruction emulation and page protection and hardware comparators. You can see that we're using the same technology that we used in 1990 to do malware analysis today. Malware analysis didn't really exist in 1990, so why are we handcuffing ourselves to the techniques of 30, 40, 50 years ago? They did talk about one interesting technique that's not new that we're starting to see echoes of today, this kind of idea of a tagged architecture. And so data tagging in the present day kind of looks like ARM is implementing this, what they call memory tagging extensions. And so you allocate something in malloc, and the top bits of memory have some permission bits. And if you ever smash that area of memory, or you try to access a pointer that doesn't have appropriate bit set, well then you trap, and you're able to detect that. But that doesn't really solve our problem of how do we set execution breakpoints. That maybe solves the problem of mitigating some memory corruption, but we're talking about something a little deeper here. And so if you take nothing else away from this talk, what I want you to remember is that debuggers today are built on hardware techniques that stopped iterating in the 90s, really. So let's start to design what might look like a solution to this problem. I'm going to borrow some goals from this Spider Breakpoint paper that I mentioned previously, because I don't want to try and start from scratch. I do want to stand on the shoulders of giants who came before me. And so I'm going to take their goals directly, and I'm going to examine where they kind of failed to solve this problem. We want our breakpoint system to be flexible. That, in their regard, they called this trap on any instruction. We want it to be efficient, which means we should run as close to real-time execution as possible. And that pretty much throws emulation out the window. We don't want to have to emulate anything. We want it to be transparent, which means we don't want a program to be able to detect our breakpoints. We don't want it to be able to see that we have changed memory in some way, or we want to prevent having to change memory at all. And we want this to be reliable, which means that if a program is resetting itself somewhere in memory or trying to evict breakpoints because it's a piece of malware, we basically don't want the program to be able to interact with the breakpoints that we've set in any way. And I'm only going to change one goal out of this whole thing. I'm going to change the flexibility goal. And the idea that I'm kind of hitting here is that instead of trapping on any instruction, I want to trap on any address, in particular without corrupting the program. And I'm going to add a bonus goal here of trying to make it work for virtual machines, because if we can scale this, that means there's high adoptability as well. So before we can really jump into the solution, we need to go do a quick refresher of some Mmu internals and talk about how VMs manage their memory as well. So the x86 Mmu works like this. Basically, there's a table, and we're going to convert this address at the top, and that address is chunked off into different offsets, and eventually we're going to drill down to a physical frame. And so you can kind of see there's this separation. There is operating system or debugger resources, and there's program resources, the actual data in the eventual physical frame. The problem that binary replacement breakpoints have is that we're jamming operating system or debugger resources into program space. And there's a trust violation here that I'll talk about in just a moment. Now, if we look at this in terms of virtual machines, I'm not going to kind of simplified view here. We have two different page tables. And one is owned entirely by the guest, and one is owned entirely by the host. You can see these as kind of your debuggee and debugger. But your data frame is still owned by kind of both, right? Because we're jamming host material into the program's data space. If we look at this spider breakpoints or DBI breakpoints, we see the same pattern reemerge again and again. We have this abstraction where we have guest data and host data, or debuggy and debugger data, but we still have a frame that is shared and it's seen as property of both. So this is the abstraction failure that we're dealing with. Basically, we have debugger data and debuggy data living in the same physical frame. And this is why the critical byte problem is present. And so the design that we're going to talk about today, we're going to just eliminate this problem altogether. And that will let us solve kind of this critical byte problem from the get-go. And so the trust failure I was talking about just a moment ago is the fact that the debugger is depending on the debuggee to play nice. That's never a good sign. And on the other side, the program is expecting the debugger not to corrupt its data, right? So if we come back and we look at the existing DBI solutions, you'll tend to see that all of them have this kind of code modification handler. And this is their attempt to solve that where is it safe to breakpoint problem because they're dealing with this abstraction problem. It's not any problem that this solution created. It's that they're fighting a problem that's existed from the 90s and no one that has really taken it up to solve it in hardware. Okay, so you get it at this point. Every other form of breakpointing is awful and I should just get on with it. So let's talk about the system that we're going to design here. First, we need to talk about the design limitations. If we want this solution to be efficient and we want this solution to be adoptable, which means that a Linux kernel will take the design in after it's been produced in hardware and actually produce something, we have to retain old behavior, which means we can't just say, throw the old system out the window altogether. We need to retain that behavior. And furthermore, it needs to be totally optional. We can't just force this new thing on everyone and say, this is the way it's going to be now. 2, we have to be able to implement this in hardware for 2 reasons. If we're going to do additional lookups or add some additional resources, in order to maintain efficiency, the translation has to be simple and it needs to be fast. And 2, we can't rely on operating system constructs because that basically means it'll never be adopted at scale. It has to be fully supportable purely in hardware, and every operating system should just be able to utilize that interface in a way that's straightforward. And 3, it has to be compatible for the TLB. And this one is a result of a few months of looking into different designs that we ultimately decided failed. But a quick look at the TLB. When you're doing a translation of a piece of virtual memory to a physical frame, you basically have this additional buffer where if you've done that lookup before, you don't have to walk the whole page table, right? But there's a limited amount of information in that TLB entry that we're going to be forced to work with. And that's basically, we have the virtual address when it comes in. We have the physical address when it goes out of the TLB. We have the permission bits, the read, write, execute bits on the page table entry. And then we have the actual page size, which we can infer from other constructs. So this is our design limitations. And this is a pretty constrained system. We're not working with very much information here. We're pretty forced to sit down at the hardware. And let's see what we can accomplish. And obviously bonus points if we can keep virtual machines in mind the whole way. So the approach that we eventually landed on after a few months of talking this through is the idea of a breakpoint frame. So kind of the high-level abstraction of what you're looking at here is we started with drawing this line where we're going to say, never shall debugger data cross this line into program data, and never shall programs being debugged be able to read across this line. In the same way that extended page tables provide that line with the guest page tables and the extended page tables, that's what we're going to apply to breakpoint data. And that naturally means that we need to allocate a second frame for breakpoint data. And we'll get into how we're going to accomplish that in a moment. But this is where the name virtual breakpoints come from. We're taking the concept of virtual memory and we're extending it to breakpoints, so hence virtual breakpoints. Now we have a mystery virtualization layer that I'm going to talk about in a moment. But before we get there, let's talk a little bit about the buddy frame that we're going to allocate. Basically, we're going to say we're going to allocate 2 physically contiguous frames per an instrumented page. So this means it is completely optional. If you don't want to allocate the frame, you don't have to. We're going to accomplish that by placing a breakpoint bit in the page table entry down at the bottom here. And if that breakpoint bit is set, then we're going to do this additional lookup. If the breakpoint bit is not set, then we don't have to do that lookup. And since we're able to apply this to the extended page table permissions, that also means that a guest operating system can't view the breakpoint data either. So we've actually, in this manner, we've solved that flexibility problem already. But what are the actual contents of a breakpoint frame? Basically, our data frame is going to contain our program data, and then our breakpoint frame is going to contain, for every byte in the program data, 8 bits of configurable data. So byte for byte parity with program data. And this seems like a lot of overhead, and we're going to go into that a little bit later, but it actually turns out to be no worse than existing systems. So what do we get to do with 8 bits of breakpoint data, right? We tend to think of breakpoints as either being read or write or executable. We want to break on instruction fetch or maybe on instruction execution. But what do we do with 4 additional bits? And this is kind of an open question, right? We can start to think about new forms of breakpoints that we can implement in a debugger. Maybe we have a taint bit that when you access it the first time, you mark that area of memory tainted by some other area of memory that you tagged previously. Maybe you have a simple coverage bit where you just want to be able to collect code coverage on a program you've instrumented. Or maybe you implement a specialty trap where if that bit is set, we're going to jump directly into a special interrupt handler that implements a very easy logging structure, right? So there's some creativity here that this opens up. And this is all implementable in hardware. Right, so what is this mystery virtualization layer that I talked about? I kind of said that the construct that we're dealing with here limits us to a limited number of information. So we have to talk about what does the translation look like. So here I've circled the key points. This virtualization layer is basically going to say, whenever this breakpoint bit is set, we're going to take our virtual address, we're going to convert it through the page table or the TLB, and we're going to get the physical address. And then we're going to simply add the page size. Right? And utilizing that, we've now identified the appropriate place in memory for our buddy frame. Right? So we've, if you remember, back to those limitations we've had, we've limited ourselves in this translation to just those small bits of information that are available in a TLB lookup. So at this point, congratulations, we did it. We designed the whole system. It kind of feels like it should be more complicated than this, right? But if you remember, I said we're borrowing the idea of virtual memory and applying that to a breakpoint frame. Fundamentally, nothing I have discussed up here is complicated enough that it requires years and years of research to determine whether or not it's going to work. It already works with virtual memory. And so the problem is that the requirements in the 80s and 90s when debuggers kind of stopped iterating didn't include things like, what if I need to reverse engineer something that's malicious? Now we have that requirement. Now we can start to look at how do we iterate on existing structures this way. So one last mention here. A common question that people kind of come up with is, how do we actually do the lookup in the breakpoint frame? In a virtual address, the very last chunk of an address is used for the offset in the frame. Right? So where normally we would access the program data, that's how we get the byte for byte parity and the lookup. So kind of circling back around and looking at our goals, right? So we set some goals for ourselves, and we set some system design limitations. Have we actually met our goals at this point? So let's start with flexibility. Can we trap on any address without corrupting the program? Well, under the old system of binary replacement, we only had the ability to interrupt on execute. And the reason for that is you actually had to execute the instruction itself, the int3 instruction, to produce the interrupt. And that's what causes that critical byte problem. You're trusting that that instruction will be there for you. With the virtual breakpoint system, we actually have the ability to either interrupt on execute or interrupt on instruction read. And that's the difference, the interrupt on instruction read. We no longer have this critical byte problem because we don't care about what's in the data frame. We're going to maybe use the microcode on an x86 processor to do this additional lookup and fire an interrupt before that instruction ever gets a chance to execute or retire in the case of speculative execution. Yeah, so we can kind of look at the system and say, at least academically, we've met our goal in that regard. But is it efficient? And this is one that most people kind of get stuck on a bit. So we need to look at two things, memory usage and execution speed. Memory usage, first of all, straight off the bat, most people go, yeah, you're sacrificing half of memory. Why are, who would use that system? But you remember, we designed this with the flexibility of use as a primary goal. So we only sacrifice a page of memory for a page that we've actually instrumented. In the worst case, where you breakpoint every page on the system, yes, you will sacrifice half of memory. But in the case of typical debugging sessions, you're going to sacrifice a couple megs at most if you're highly instrumenting your program. That's nothing. And on the topic of execution speed, the additional memory lookup per memory access is a pretty high overhead. But again, this only happens on pages with breakpoints. On prior systems, this code modification handler and this different view of memory forced you to exit the program for every access on a page already. Now, instead of exiting the program and introducing all of that additional overhead, we're simply adding an additional memory lookup and bypassing that altogether. So it's a matter of you're amortizing the cost in this regard. And you're getting rid of a whole lot of old instrumentation that we have had to hack around. OK, so academically speaking, we've at least addressed the efficiency issue. But have we solved the transparency and the reliability issue? Kind of interrelated. So in the transparency of virtual breakpoints, the problem that they solved with that code modification handler was the fact that you were sharing that data frame. Now we no longer share that data frame. And if we look at this abstraction and we think about it in terms of a hypervisor, there's no crossing that line with regards to the same page table construct. So now the debugee only has access to its own data, and the debugger, it could implement normal binary breakpoints this way, but it also has the construct to be able to completely remove that from the data frame, which means that the debugee can't interact or see the breakpoints in any way. So we've addressed the transparency problem. Now, are these reliable? So if we look at this critical byte problem one more time, we can kind of see if we breakpoint a place in memory, and then let's say this program is malicious and it kind of shifts itself in memory just by a couple of bytes. We have to evict the breakpoint and fall back to emulation because we're dealing with that critical byte problem. If you just programmatically set the breakpoint right where it was, again, you corrupt the program. So that's not very reliable. But with a new construct that provides this virtual breakpoint system, we end up being able to subvert this issue by doing breakpoint on instruction fetch instead of instruction execute. And that means we can breakpoint in the middle of an instruction, and when that data is fetched, we'll just breakpoint anyway. If you remember, the demo I showed you had two problems. One, we changed the program, and two, we didn't break into the program. So now we've solved that problem here. And that's really the huge kicker. All right, and so have we also addressed making this work for virtual machines? Yeah, because we discussed that pretty much the whole way through. We designed it with basically extended page tables in mind the whole way. So some of you are probably sitting in the crowd going, wait a second, there's a problem here. You're giving a talk where you have essentially nothing to show us because there's no proof of concept. And that's the big fat problem here. And that's the big fat problem that the question here is ultimately, I'm proposing an extension to the x86 MMU. How does a lonely engineer go about producing an example to show that that works? There are ways that you can do that. For example, we could prototype this system in a simulator or an emulator. I could spend a couple of years implementing all the debugger constructs that I talked about and implementing the support in the Linux kernel to support the underlying stuff, all built on top of an emulator. But ultimately, that's not very useful. That's, in the way I would put it, is kind of lame, because ultimately I've just spent a couple of years building something that no one's ever going to use. It's not efficient enough to do real research. Better off just using a normal hypervisor. And that means it just won't be adopted. I could, and I've gotten this suggestion a number of times, implement this system on RISC-V or maybe ARM or any other form of RISC. But I kind of started this talk talking about x86. I want to solve this for x86. But OK, I take the point. I could do that. But there's two problems here. One, it's a RISC. There's no critical byte issue. You can just set your breakpoints on aligned data and know that they're safe to set, at least theoretically anyway. But two, most RISC-V chips lack a real MMU. And the reason why I pick on RISC-V here is the fact that that's really the only open source thing that I can work on, as opposed to ARM, which is not necessarily as available. And three, the major point, it's not x86. I really want to solve this for x86. And the reality is I can't. There's actually kind of an interesting program that I ran up against in the past few months at another conference called Intel HARP. It's this hardware accelerated research program where Intel actually provides certain institutions a preview of their upcoming hardware with FPGAs attached to it so that you can implement new kinds of instructions and maybe implement extensions to the system like a barrier. I was introduced to this based on a paper I found at a conference that was recently published. But there's problems with this too, and the big one is there's no access to the MMU or TLV hardware at all. So the one thing that you would need to implement or produce a prototype of this using the Intel HARP program is not available because it's very close source. It's IP for them. And so there's also only a few installations that have this available to them. I believe there's a way to buy into this program for anyone that's curious, but there is limited accessibility based on that cost. And the last one is kind of going out and seeking buy-in from Intel and AMD. And I kind of posit that question to the audience here. If you're a researcher that finds a problem like this and comes up with a solution, but the solution is only possible to solve, and it's only possible to implement it in hardware, how do you pitch that to Intel or AMD and have, maybe I get the CIO's phone number and I call him and I say, I have a really cool invention for you. And he's probably going to be like, who are you and how did you get my number, right? So how does an engineer who's doing research on this and finds this problem solve this issue? And I don't have an answer to that. And so if that's kind of a community problem. It's kind of a problem that we don't discuss very often. When we find problems, we think about Meltdown Inspector. It has to take that level of a problem for anything to get addressed at that level. And that's a problem. We need a better agile solution in that regard. One last thing. This is kind of, as I was going through the development of this, I had a few people say to me, hey, you should actually patent this design because while it borrows some areas from other places, it's definitely novel in the sense that I couldn't find a single implementation going back to the 70s that implemented a system like by doing this. So I wanted to bring up two things. One, I could have submitted a patent on this about 2 years ago before I decided to publish it. And there's two sections of the patent law that are to be concerned with. Basically, one, you can do any amount of private research you want, and until you decide to go public, you can file a patent on it. There's no bar date in that regard. But once you go public with it, you have 1 year to file a patent. Doesn't matter if it's you or someone else. At that point, it is first to file. So I published this paper originally on archive.org in about 2017, and I did nothing with it, and I just waited. And after about a year, I was like, OK, now we'll go talk about it. Because now, no one can take this design, patent it, and turn it into their IP. And so if anyone at Intel or AMD is watching, just take it, please. I just want to solve the problem. I just want to not deal with this headache anymore and make new fun debuggers. And so at this point, that's the end of my talk. If you guys have any questions, I'd love to answer them.
Wait. Can you repeat that?
Would you be able to implement what you're talking about instead of having the big guns make the hardware for you, and like in a card you could put on PCI bus or something?
Yeah, so I presented one possible solution here. I kind of stopped the research after we came to the conclusion that there was going to be a hardware component. Once we decided that probably the most efficient way of implementing this would be as an MMU extension, there isn't really much you can do external to the MMU and still make it efficient. You have to have a software component involved if there's an external card, right? Because what happens when the instruction retires, for example, and then your external card decides to fire an interrupt? Well, you've already passed the breakpoint spot. So I'm not claiming that there isn't another way to do this. If someone could come up with another way of doing it, I'd be all ears. And especially if it doesn't involve having to get highly embedded with Intel, but that's the limitation that I see. Someone else have?
Have you considered any security implications of adding this kind of hardware into a device?
I have thought about it a little bit, but the reality is until you have an implementation or a prototype, it's kind of hard. You're speculating. So as a process of the hardware design, as a process of the extension design, there's probably a lot of room to talk about that. But that goes beyond the immediate topic of this talk. So it's a very good question, but no, basically, I haven't. It kind of goes back into the abstract of the talk said that there's kind of this cat and mouse game between debuggers and malware. And that goes to that. What happens when we produce a new construct that malware does not even have an idea about? And so that's where I think we would kick that back into high gear. But that's kind of the limit at where I'm at. Anyone else? All right.
So you said there was no value in implementing some kind of emulator version of this, but if you were to build something like this into QEMU, and then you could show results of how much,
sure.
Yeah, wouldn't that not make a much stronger case to Intel, AMD?
Sure. I would actually argue that it's relatively simple to implement this in QEMU. You simply, on any instruction fetch, check to see if you have a breakpoint set in some other page, right? It's not an interesting solution there, and I'm pretty sure someone has probably done that exactly. But implementing the whole construct of the MMU extension doesn't really make sense in an emulator sense, if that makes.
It sort of makes sense.
Right, so like I can just allocate a secondary page for every single page in the system, and on every access to memory, I can just check that. Like I've just designed the whole solution in QEMU in a really naive sense, but the overhead is going to be too high for it to be useful to anyone. I think there was a question here.
Where? Oh,
right over here.
So how has no one run into this before?
Right.
How often are you seeing this?
That is a great question. I kind of go back to this slide that I had that talks about the history of breakpoints. And it's a question that I get pretty commonly when I talk about this issue. Basically, when did someone last review this technology? As far as I can tell, everyone in the industry has just kind of said, well, these are the tools we have, so that's what we're going to use. That's what's available to us. And that's how you end up with these kind of systems. It's not that these systems are bad. It's that they recognize the problem is there, but they don't think that that's a problem they should try to solve or that they should even talk about. That's the intent of this talk, is to say, here's this problem. It's been going on for 50 years. People are acutely aware of it because they implement the code modification handler to the system. But no one ever talks about, hey, should we actually try to solve that issue? They say, well, the way I would put it is we're all kind of Stockholm syndrome with regards to the x86 platforms, right? Whatever they say will exist is what exists, unless you have the resources of a Microsoft or an Apple. Any other questions? Did that answer your question?
So I'm not sure how it works, like upgrading a, x86. So suppose Intel decides that they want to implement this or something like it. Like, how does backward compatibility work? Would it only be working in new generations of Intel CPUs, or would it be backwards compatible?
Yeah, so backwards compatibility in the sense that being able to provide, where's the design? Sorry, just a moment, I'll pull this up. It kind of comes back to this picture here. In the sense that moving forward, any chips that had this construct available to them, you need that additional virtualization layer here that does the translation kind of basically in microcode. Because if you try to solve it in software, you have existing constructs that cause this problem. So older chipsets that didn't have that extension and weren't able to solve this in microcode wouldn't be able to implement this. But we retain all the old behavior, right? So any software that was built expecting the old behavior would still be able to operate. So that's one of the ideas that I said that one of the design constraints that we had to apply to thinking about the system was we can't just tell people that old way of doing things is dead, because that's how you kill your adoptability from the get-go.
Do you have any evidence that a microcode update could or could not implement this?
I don't, and that's why I say that I think that's kind of where the limits of my knowledge of kind of that low level in terms of AMD or Intel are limited. I'm by and large a hypervisor developer, not a hardware developer. So the idea that they could implement this in microcode is entirely possible. Cool. Thanks very much.